Hello. Welcome back to another super amazing video. The experiment we performed of tying a string perfectly around a sphere was tedious, but that was done only to be absolutely precise with the calculations. If we just want to explore the idea of surface area of a sphere and not be too precise about it, we can perform a simple experiment with an orange. We take an orange and measure its radius using a ruler. Then, on a piece of paper, we draw a line of the same length as the radius of the orange. Next, we take a compass and adjust its arms to match the length of the line in order to draw 4 circles with the same radius as the orange. Once the 4 circles are drawn, we peel off the orange bit by bit and use each of those bits to cover the area enclosed by each of the 4 circles completely. We would see that eventually the pieces of the peel would cover the 4 circles almost perfectly. And now that we have seen 2 versions of the same idea, we can be 100% sure that the total surface area of a sphere is 4 times the area of a circle with the same radius as the sphere. And the area of a circle of radius r is just pi r squared. So, the total surface area of a sphere is 4 times pi r squared, which is 4 pi r squared. Here, r is also the radius of the sphere. Now, because the entire surface of a sphere is curved, its total surface area is the same as its curved surface area. But the same does not hold true in case of a hemisphere because of this flat base. For a hemisphere, its curved surface area is equal to 2 pi r squared and its total surface area is equal to 2 plus 1, that's 3 pi r squared. So, now that we have recapitulated the concepts as well as the formula, let's get down to using them and solving some really interesting problems. Excited? Let's roll. As always, we'll start with a perfectly simple question. Say this one. It states that a right circular cylinder perfectly encloses a sphere of radius r, and we just have to find the ratio of the curved surface areas of the 2 shapes. Pretty simple and straightforward, right? There's a right circular cylinder and a sphere. We have to calculate each of their curved surface areas and then compare them to calculate the ratio between the 2. If you notice, you will be able to see that there are no numbers available in the question. It is actually just a test of your understanding of the concept. So, let us see what the trick is in this one. Now, the question tells us that the right circular cylinder perfectly encloses the sphere. So, when we do that, it becomes pretty evident that the radius of the cylinder is the same as that of the sphere. Now, for a sphere of radius r, its curved surface area is calculated using 4 pi r squared, and for a cylinder of radius r and height h, its curved surface area is calculated using 2 pi r h. Now, what do you think would be the height of this cylinder? Whatever it is, it's going to be the same as the diameter of the sphere, right? So, we can say that h is equal to 2r. Now, on substituting this value of h in this formula, we get the curved surface area of this right circular cylinder is equal to 2 pi r into 2r, which is 4 pi r squared. See, both the curved surface areas turn out to be the same. We saw this in the previous video, remember? You should have been able to solve this almost instantly. But no worries, try to remember next time. For now, since both the curved surface areas are the same, the required ratio is just 1:1. Let us now look at something more interesting. Say this one. It states that the internal and external diameters of a hollow hemispherical vessel are 24 centimeters and 25 centimeters respectively. The cost to paint 1 square centimeters of surface is rupees 0.05, and we have to find the total cost to paint the vessel over. Understood the question? It talks about a hollow hemispherical vessel with internal and external diameters, right? So, this hints that the hemispherical vessel has some thickness, pretty much like this. Looks like a boat. So, the internal diameter, which is this one, is given as 24 centimeters. And the external diameter, which is of course this one, is given as 25 centimeters. The rate of painting is available, and we just have to find the cost of painting the complete surface of the vessel. Got a clearer picture now? Great. Let's get to the solution. To calculate the cost of painting the complete surface of the vessel, we first need to know the area of the complete surface, right? So basically, we need to find the total surface area of this hemispherical vessel. Now, this vessel consists of this outer part, this inner part, and most importantly, this ring on the top. So, its total surface area would be the outer surface area plus the inner surface area plus the area of the base ring. Now, the outer and the inner surface areas can be calculated very easily. The external and internal diameters are available, so having them would give us the external and the internal radii, say capital R and small r respectively. And once the radii are known, we can substitute their values in this formula to get the two areas. The outer surface area would be 2 pi capital R squared and the inner surface area would be 2 pi small r squared. But how do we find the area of this ring? We have studied this before, remember? We just covered this hollow part in a different color to get a big disc with the same radius as that of the external radius. Now, when we subtract the area of this small disc from that of the big disc, we of course get the area of this base ring. So, the area of the big disc is of course pi capital R squared, and that of the small disc is evidently pi small r squared. So, the area of this ring is equal to pi capital R squared minus pi small r squared. Now, we agreed that the total surface area of this hemispherical vessel is the outer surface area plus the inner surface area plus the area of the ring. So, on using the respective formulae in this equation, we get the total surface area of this hemispherical vessel is equal to 2 pi capital R squared plus 2 pi small r squared plus pi capital R squared minus pi small r squared. On simplifying this, we get the total surface area is equal to 3 pi capital R squared plus pi small r squared. Now, when we take pi common, we get the required area is equal to pi into 3 capital R squared plus small r squared. Now, we know that capital R would just be 25 by 2 centimeters and small r would be 24 by 2, that's 12 centimeters. So, on substituting these values and then using pi is equal to 22 by 7, we get the required area is equal to 22 by 7 into 3 into 25 by 2 whole squared plus 12 squared square centimeters. Whoa, quite nasty, isn't it? So, on multiple levels of simplification, we finally arrive at 26961 by 14 square centimeters. So basically, the total surface area of this hollow hemispherical vessel is 26961 by 14 square centimeter. Now, the cost of painting 1 square centimeters of surface is rupees 0.05. Then, the total cost of painting the complete surface would be rupees 0.05 into 26961 by 14. Now, this just simplifies to rupees 96.29. So, it just takes rupees 96.29 to paint the complete surface of this hemispherical vessel. Hey, we are at the end of this video already. I hope you enjoyed solving problems on the surface areas of spheres and hemispheres. By now, we have developed a pretty solid idea about each of these shapes. But trust me when I say we have just scratched the tip of the iceberg. There's a lot more to be learned about each of these shapes, including their respective volumes. That is something that we'll be discussing in the next video. For now, I recommend that you go and solve problems in the quiz section. I'll be seeing you super soon with another amazing video. Till then, stay amazed and stay amazing.